Welcome back to the Sleepy Geographer channel, a place where the maps of the world unfold slowly, fact by fact, ridge by ridge. Tonight we leave the sun-baked dunes for a landscape of a different extreme. We journey to the realms of silent, moving ice. In the high, thin air of the world's great mountain ranges and across the vast polar deserts of the poles, there exist rivers of a most peculiar kind. They do not babble or rush. They do not sparkle under the sun in quite the same way. Their currents are not measured in minutes or miles per hour, but in centuries and inches per year. These are the rivers of ice, the glaciers. To stand before one is to feel a certain kind of silence. It is a deep, resonant quiet, broken only by the wind and the occasional echoing crack that seems to come from within the earth itself. They appear as frozen landscapes, static and immovable, great tongues of white and blue spilling from high cirques into valleys below. But this is an illusion, a trick of our own hurried perception. For what we are seeing is not a frozen snapshot, but a moment in a continuous slow-motion cascade. A flow of ice so patient, so persistent, that it defies everything we know about the nature of solid matter. This is the silent journey, a journey that begins not with a roar, but with a single, delicate snowflake. Imagine the highest, coldest reaches of a mountain range, a place where the air is sharp and the storms are frequent. Here, snow falls season after season, year after year. It settles on north-facing slopes and in sheltered bowls where the summer sun cannot fully reach it. The first winter's snow is followed by the next, and the next, layering upon itself like the pages of a book being slowly written. The weight of each new storm presses down on the layers beneath. This pressure, gentle at first, but accumulating over time, begins a remarkable transformation. The delicate hexagonal arms of the snowflake collapse. The air between the crystals is slowly squeezed out. What was once light, powdery snow becomes a denser, coarser material called firn, a granular, sugary snow that is the adolescent stage of glacial ice. And with more time and more weight, the firn grains are pressed even closer. They begin to fuse, to recrystallize into a solid, monolithic mass of ice. But this is not the clear ice of a winter pond. This ice is different. It is dense, and it holds within it a secret. Tiny trapped bubbles of the ancient atmosphere, and a peculiar property that allows it to behave not like a brittle pane of glass, but like a thick, viscous fluid. It is this ice, born from countless winters, that begins to feel the irresistible pull of gravity. The glacier, now a body of ice perhaps hundreds of meters thick, begins to move. It is not a slide, but a slow, internal deformation. The ice, under the immense pressure of its own weight, actually flows. Molecules shift past one another. The entire mass oozes downhill, conforming to the contours of the land, a river of solid water seeking its lowest level. It is a movement so gradual that it is invisible to the naked eye. If you were to place a stone on its surface and return a year later, it may have moved only a few dozen feet. But over a human lifetime, that stone would travel a significant distance. Over a millennium, it would journey for miles. This movement is the glacier's heartbeat, its silent, steady pulse. It is what transforms a static accumulation of snow and ice into a dynamic force of nature. A glacier is not a thing, but a process, an event that is always happening, and as it moves, tells a story. The blue color you see deep in the crevasses is not a trick of the light, but a testament to its age and density. Air bubbles are compressed to near nothingness, and the ice absorbs all colors of the spectrum except for blue, which it scatters back to our eyes. The deeper the blue, the older, the more compressed, the more pure the ice. It is the color of time itself. To witness a glacier is to look into the past. The ice at the head of the glacier may have fallen as snow thousands of years ago. It has been compacted, buried, and has begun its slow, inexorable journey downward. It carries with it dust from long ago volcanic eruptions pollen from extinct plants, and the very air that ancient humans and animals breathed. It is an archive, a frozen library of the planet's history, slowly making its way to the present day. So, as we begin this exploration, we must first adjust our sense of time. We must learn to see the movement in the stillness, to hear the flow in the silence. The journey of the glacier has already been underway for millennia before we arrived. We are merely stepping for a moment into its current, to understand its origin, its path, and its ultimate fate. This is not just a story of ice, but a story of the Earth's memory, written in water and stone, and moving with a patience that humbles all who take the time to observe it. The silent journey has begun, and we are here to listen. That silent, flowing river of ice we began to observe does not simply appear. It is born from the most ephemeral of materials, a snowflake, the transformation of a single, delicate crystal into the dense, plastic ice of a glacier is an alchemy of time and pressure, a recipe written not in fire but in cold. Imagine the highest, coldest reaches of a mountain range. A fresh snowfall has just settled, blanketing the world in a soft, pristine silence. Each snowflake is a tiny, intricate crystal, a six-pointed star of exquisite geometry. It is fragile, airy, and full of space. A handful of this new snow is mostly air, a temporary sculpture destined to melt or sublimate away. This is the raw ingredient, but this snowfall is not the last. Another storm arrives and then another. The weight of the new snow begins to press down upon the old. The delicate points of the snowflakes below start to fracture, to sinter, to nestle closer together. They lose their intricate individuality, merging into a more granular, cohesive layer. This is the first transformation. The light, powdery snow becomes what is known as neve, or fern, a German word meaning of last year. It has the consistency of coarse, wet sugar, and it crunches underfoot with a distinct sound. It is snow that has survived a full melt season, the first sign of permanence. Yet this is still only the beginning. The fern is young, porous, and white, but the layers continue to build. Season stacks upon season, decade upon decade. The weight of hundreds, then thousands of feet of accumulated snow and fern becomes immense. This pressure is the primary sculptor. It forces the fern grains ever closer, squeezing out the tiny pockets of air that separate them. Slowly, a remarkable process begins. Regulation. The points of contact between the individual fern grains experience such immense pressure that they melt at a microscopic level. The water from this microscopic melt then flows into the tiny spaces between the grains and refreezes. This melting and refreezing cements the grains together, welding them into a solid, dense mass. The air bubbles become trapped, tiny, isolated prisons of the atmosphere from the time the snow fell. Over time, which may span decades or even centuries, the fern is compressed into solid ice. The transformation is complete. What was once a fluffy, ephemeral snowflake is now part of a dense, crystalline structure. The white color fades, replaced by a translucent, often blue hue. The air content drops dramatically. The ice itself becomes a substance that can flow, a plastic solid under the relentless force of its own weight. This process is a gradual continuum. There is no single moment when snow becomes ice. It is a journey of compaction, a slow and inexorable closing of space. It is a testament to the power of patience, to the fact that even the softest, most transient of materials, when subjected to enough time and enough pressure, can become one of the most powerful and enduring forces on our planet. The recipe, then, is deceptively simple. The ingredients are atmospheric moisture and cold. The method is to apply pressure and weight. It is a process that requires no human hand, only the patient, cyclical turning of the seasons and the unwavering pull of gravity. So the next time you see a photograph of a glacier's deep blue heart, remember the journey that connects it to a cloud of delicate, floating stars. A glacier, for all its monolithic appearance, is not a uniform sheet of ice. It is a dynamic system, a living entity with distinct parts that function in a delicate, perpetual balance. To understand its life cycle, we must dissect its anatomy, not with a scalpel, but with our gaze, learning to read the subtle signs on its vast, white canvas. A glacier breathes. It has a region where it gains mass, and a region where it loses it. Its very existence hinges on the tension between these two states. High up, near the head of the glacier, lies its heart, the zone of accumulation. This is typically a broad, high-altitude basin, a cirque, sheltered from the full force of the sun, where the air is thin and cold for most of the year. Here, the glacier is fed. Winter storms deposit more snow than the brief summer can melt. This is where the recipe we learned earlier is perpetually underway. Fresh snow transforms to fern, and fern to glacial ice. The landscape here is often a pristine, rolling white field, though it may be scarred by deep, hidden crevasses. This zone is the glacier's savings account, where it builds its capital of ice, the reservoir of mass that will fuel its slow journey downhill. The ice here is younger, less compressed, and often whiter, still holding the memory of recent snowfalls. Without a robust zone of accumulation, a glacier cannot survive. It is here that its life begins anew each year. Conversely, at its lower, warmer end, we find the zone of ablation. The word ablation comes from the Latin for to carry away, and it is here that the glacier's substance is carried away by sun, rain, and wind. This is the domain of loss. In the ablation zone, the summer melt exceeds the winter snowfall. The ice here is older, having travelled from the heights, and it is in its final act. The surface becomes dirty with rock debris that has fallen from the surrounding valley walls. It is often marked by a chaotic topography of meltwater streams, deep blue pools, and a rough, pitted surface. The most obvious feature of this zone is the terminus, or snout, of the glacier. Its leading edge, the final front in its slow battle against the climate. Here, the ice simply melts away, often dripping into a milky, sediment-laden stream that becomes the headwaters of a river. In some cases, if the glacier meets the sea or a lake, the terminus is a towering wall of ice from which icebergs carve into the water with dramatic, thunderous breaks. The boundary between these two fundamental zones is not a sharp line on a map, but a conceptual one, though it has a physical manifestation, the equilibrium line. This is the altitude on the glacier, where the amount of snow gained in the winter exactly balances the amount of ice and snow lost in the summer. It is a fleeting balance, a line that shifts from year to year, a sensitive barometer of the glacier's health. Above this line, the glacier grows thicker. Below it, it grows thinner. In a healthy, stable glacier, the equilibrium line remains in roughly the same position over time. The ice that accumulates in the high basins flows downward, replacing the ice that is lost to ablation at the terminus. The glacier is in a state of dynamic equilibrium, like a conveyor belt. Ice is constantly moving from the zone of accumulation through the equilibrium line and into the zone of ablation, where it is eventually removed. The surface of the glacier tells this story visually. In the accumulation zone, the snow from the previous winter often remains, covering the older ice beneath. As you travel down glacier and cross the equilibrium line, you begin to see the older, dirtier ice of the previous years exposed at the surface. This transition is often stark, a clear line between white and grey. The height and shape of the glacier also reflect this anatomy. The accumulation zone is typically thicker and broader, while the ablation zone often thins and narrows as it wastes away. This balance between accumulation and ablation dictates everything about a glacier's behavior. If the climate cools or snowfall increases, the zone of accumulation expands. The equilibrium line shifts to a lower altitude. The glacier gains more mass than it loses, and it responds by thickening and advancing, its terminus pushing forward down the valley. It is growing, but if the climate warms, the opposite occurs. The zone of ablation expands, reaching higher up the mountain. The equilibrium line climbs to a higher altitude. The glacier loses more mass than it gains. It begins to thin and retreat. The terminus melts back uphill, not because the ice is flowing backward, but because the melting at the snout is happening faster than the ice can flow forward to replace it. The conveyor belt is still moving, but the end of the line is being dismantled more quickly. The new product arrives. This is the state of most of the world's glaciers today, in a painful, visible retreat. Therefore, to look at a glacier is to see a snapshot of a climatic equation. Its length, the position of its terminus, the altitude of its equilibrium line, these are not arbitrary features. They are the direct result of the long-standing battle between winter's gift of snow and summer's demand for melt. The glacier is an accountant, meticulously recording the balance of its energy budget in the very shape of its body. It is a giant whose anatomy is not fixed, but fluid, constantly reshaping itself in response to the whispers of the atmosphere. Its silent flow is a language, and its zones of accumulation and ablation are the key phrases in its long, slow story of survival. We have seen how a glacier is born from snow, and how its body is divided into zones of gain and loss. But this static anatomy belies its true nature. The essence of a glacier, what makes it a river and not a lake, is its motion. This movement is not a sudden, brittle cracking, but a deep, persistent flow, a pulse that beats over centuries. It is a movement so slow and viscous that it challenges our very definition of a solid. The first and most fundamental mechanism of this flow is internal deformation. Imagine the immense weight of ice we discussed, hundreds of meters thick, pressing down upon itself. Under this colossal pressure, the ice crystals themselves begin to change. They are not rigidly locked in place. Instead, they slowly deform. Individual molecules within the crystal lattice shift past one another, and the crystals can even rotate and recrystallize. This happens not because the ice is melting, but because of the relentless steady stress. The entire ice mass behaves like a thick plastic material, like putty or hot glass, slowly sagging over time. This internal flow is greatest at the base of the glacier, where the pressure is most intense and decreases toward the surface. It is the silent, invisible oozing that carries the glacier forward from within its own depths. But internal deformation is only part of the story. For many glaciers, a second, more dramatic process is at work: basal sliding. This occurs when the glacier is able to slide over the bedrock beneath it. For this to happen, a crucial condition must be met. The ice at the very base must be at its pressure melting point. The tremendous weight of the overlying ice can lower the melting point of ice just enough for a thin film of liquid water to form at the contact with the bedrock, even if the overall temperature of the glacier is below freezing. This layer of meltwater acts as a lubricant, allowing the entire mass of ice to slide over its foundation. The journey is not smooth, however. The bedrock is rarely polished and even. It is rugged, torn with bumps and ridges from the glacier's own past erosive work. How does the ice navigate this rough terrain? Through two clever subsidiary processes. The first is enhanced basal sliding. When the ice encounters a bedrock obstacle, the increased pressure on the upstream side of the obstacle can cause localized melting. This meltwater flows around the obstacle and refreezes on the downstream side, where the pressure is lower. This process, called regulation, effectively allows the ice to slide past the obstacle by melting on one side and freezing on the other. The second process is bed deformation. In some cases, especially with glaciers that overlay soft, water-saturated sediments, the glacier doesn't just slide, it actually drags the slippery, malleable ground along with it. The glacier's bed itself becomes part of the flowing system. The rate of this glacial pulse is not constant. It varies with the seasons. During the warm summer months, meltwater from the surface cascades down through crevices and moulins, deep, vertical shafts in the ice, delivering a surge of water to the glacier's base. This greatly enhances basal sliding, causing the glacier to literally speed up in a phenomenon known as a summer surge. The glacier's pulse quickens. In the winter, when this surface meltwater supply is cut off, the sliding slows and the glacier returns to its more stately, baseline pace governed primarily by internal deformation. This motion also dictates the glacier's surface character. Ice does not flow uniformly. The center of a glacier, away from the frictional drag of the valley walls, flows faster than its edges. Similarly, the top of the glacier, less constrained, flows faster than the bottom, which is gripped by friction with the bedrock. This differential flow is what creates the glacier's most dramatic surface features, the deep, gaping crevasses. These cracks are not signs of the ice breaking in a brittle sense, but rather they are tears that form when the ice is stretched faster than it can deform plastically. They are the visible evidence of the immense stresses at work within the flowing ice, the stretch marks on the skin of the giant. So, when we observe a glacier, we are not looking at a frozen monument. We are witnessing a profound physical paradox, a solid that flows. Its movement is the direct expression of gravity's pull on its immense mass. It is a response to the relentless pressure that transforms brittle ice into a souching substance, and to the subtle physics of water that lubricates its path. This pulse of motion is what connects the accumulation zone to the ablation zone, what transports the ice from its birthplace to its eventual demise. It is the heartbeat of the giant, a slow, powerful rhythm that shapes not only the ice itself, but the very landscape through which it moves. It is a pulse so gradual that we cannot perceive it in a moment, but over time its power is absolute. The smooth, white expanse of a glacier's surface is an illusion, a blanket thrown over a world of profound fracture and strain. As the river of ice flows, it is stretched, twisted, and compressed by the uneven terrain beneath it and the varying speeds within its own body. It cannot always adjust to these stresses with its slow, plastic flow. When the strain becomes too great, the ice behaves as the brittle solid it ultimately is, and it cracks. These cracks are the crevasses and seracs, the dramatic, often hidden vocabulary of a glacier's struggle with its own motion. A crevasse is more than just a crack in the ice. It is a profound tear, a deep wound that can plunge hundreds of feet into the glacier's heart. They form because the ice is being pulled apart faster than it can deform internally. Imagine a slow-moving river of honey poured over a series of bumps and curves. The surface of the honey would develop ripples and tears. A glacier does the same, but on a monumental scale and at a pace so slow it is imperceptible. The location and orientation of a crevasse reveal exactly what kind of stress the ice is under. The most common type are transverse crevasses. These arc across the glacier perpendicular to the direction of flow. They occur when the glacier flows over a steep slope in its bed. The ice stretches as it speeds up down the incline, and the surface cracks like the skin of a drum being tapped. Walking across a glacier, a field of transverse crevasses, is a clear sign that you are moving down a significant step in the valley floor, a topography hidden far below the ice. Then there are longitudinal crevasses which run parallel to the flow. These open up when the glacier is spreading out or stretching widthwise, often as it moves from a narrow valley into a broader basin. The ice is essentially being pulled apart from its sides. Conversely, compressive flow, where the glacier is slowing down, perhaps as it meets a flatter plane, does not typically create crevasses. Instead, it scrunches the ice up, creating pressure ridges and folding the existing layers. Perhaps the most treacherous are marginal crevasses, also known as border crevasses. These form at an angle to the flow, starting at the glacier's edge and curving upstream. They are the result of shear stress. The center of the glacier is moving faster than its edges, which are dragged down by friction with the valley walls. This difference in speed tears the ice diagonally. These crevasses are particularly dangerous because they are often hidden by snowbanks that accumulate at the glacier's margin, forming unstable snow bridges that can collapse under the lightest weight. But the most awe-inspiring and unstable formations are seracs. These are towering pillars or blocks of ice that stand between intersecting crevasses, often found on steep icefalls. An icefall is the glacial equivalent of a waterfall, a section where the glacier flows over a precipitous cliff in its bed. Here, the ice is stretched, shattered, and chaotically rearranged as it tumbles down the slope. A vast jumble of seracs is created, a chaotic city of ice pillars, some as large as cathedrals, all precariously balanced. They are constantly shifting, melting, and collapsing. The sound of a serac breaking off, a deep, groaning crack followed by a thunderous roar, is one of the most powerful and humbling sounds in the natural world, a stark reminder of the glacier's raw, unstable power. The life of a crevasse is as dynamic as the glacier itself. New ones are constantly forming as the ice moves. Older ones may be closed shut by compressive flow, their walls squeezing together until the fracture is healed by the pressure, leaving only a scar of debris in the ice. Others are pulled wider and deeper over time. Their surfaces are rarely clean. Wind-blown snow collects on their edges and meltwater carves smooth, flowing curves into their walls, giving them a sculpted, organic appearance. At their bottom, a strange blue light often glows, filtered through the ice, creating an atmosphere of unearthly beauty that belies the danger. For any who travel across them, crevasses and seracs represent the ultimate hazard. They are the reason glaciers must be navigated with ropes, skill, and profound respect. A hidden crevasse bridged by a deceptively strong-looking layer of snow can be a trap. They are the glacier's defenses, its way of reminding us that its serene, white surface is a mask for a landscape of constant change and immense force. These fractures are not signs of weakness, but of strength and activity. They are the visible expression of the immense energies working within the flowing ice. A glacier without crevasses would be a glacier that is not moving, a glacier that is dead. The cracks in the glass are therefore a testament to life, a turbulent, dangerous, and breathtakingly beautiful life. They are the glacier's own language, spelling out in lines of deep blue and white the story of its arduous, grinding journey down the mountain. To walk through a high alpine valley is to walk through a sculpture gallery shaped by ice. The most profound and unmistakable signature of a glacier's past presence is the valley it leaves behind. Unlike the sharp, angular valleys carved by rivers, a glacial valley has a distinct, graceful, and monumental form, the U-shape. It is a trough of breathtaking scale with broad, steep walls and a wide, flat floor. This iconic shape is not an accident of geology. It is the direct result of a glacier's unique and relentless method of excavation, a slow, grinding artistry that operates with the force of a continent. The transformation begins with a pre-existing landscape, typically a V-shaped valley carved by a river. Rivers, focused on cutting a narrow, efficient path for water, dig downward. Their valleys are deep and narrow, like a crack etched into the earth. When a glacier forms in the mountains and begins to flow, it does not follow the river's delicate incision. It is far too massive, too ponderous to be contained. It fills the entire river valley, and then some. Its immense weight and breadth pressing against the valley walls with unimaginable force. The glacier then becomes a master sculptor, employing two primary tools. The first is plucking. As the glacier moves, its base melts slightly from the pressure against the bedrock. This meltwater seeps into cracks and fractures in the rock. When it refreezes, it expands, prying loose boulders and fragments of bedrock, effectively locking them into the ice at the glacier's base. As the glacier continues its flow, it literally plucks these rocks from the valley floor and walls, incorporating them into its frozen body. This process is particularly effective on the downstream side of rocky obstacles, where the ice tears away chunks of the landscape. The second, and perhaps more abrasive, tool is abrasion. The rocks plucked by the glacier, ranging from fine grains to massive boulders, become cutting tools embedded in its base. As the ice grinds forward, this rough underside acts like a colossal sheet of sandpaper, scraping and scratching the bedrock beneath. The entire mass of the glacier, often thousands of feet thick, provides the pressure, turning these embedded rocks into powerful gravers that scour the valley floor and polish the walls. The evidence of this sanding is everywhere in a U-shaped valley, in the smooth, polished rock surfaces that gleam in the sun, and in the long, parallel scratches known as striations that line the valley walls, indicating the precise direction of the ice's flow. This combination of plucking and abrasion fundamentally reshapes the landscape. The glacier is not a precision instrument. It is a bulldozer of continental proportions. It does not merely deepen the valley, it widens it. As it flows, it chews away at the sides, straightening the winding course of the original river valley, grinding down interlocking spurs of rock that once jutted into the river's path. The result is a valley that is straighter, wider, and deeper than its river-carved predecessor. The cross-section becomes a broad, sweeping U, because the glacier's erosive power is concentrated across its entire base, not just a single thread of water. The scale of this carving is almost beyond comprehension. The pressure exerted by a thick glacier is sufficient to reshape the very crust of the Earth, a phenomenon known as glacial isostatic adjustment. The weight of the ice is so great that it can depress the bedrock beneath it by hundreds of meters, while the land eventually rebounds after the ice melts. A slow, ongoing process still happening today in places like Scandinavia and Canada. The U-shaped valley remains as a permanent testament to the ice's colossal burden. Within these grand valleys, smaller features tell more detailed stories. Hanging valleys are perhaps the most dramatic. These are smaller U-shaped valleys left by tributary glaciers that flowed into the main, larger glacier. Because the main glacier was so much more massive and erosive, it carved a much deeper trough. When the ice melted away, the smaller tributary valleys were left suspended high on the walls of the main valley, often with spectacular waterfalls cascading from their mouths down to the main valley floor. These waterfalls are the direct offspring of the glacier's unequal carving. The very head of the U-shaped valley often culminates in a steep, imposing wall, known as a head wall or trough end. This is where the glacier began its work, plucking and quarrying rock from the cirque at its source, carving backward into the mountain in a process called headward erosion. To stand in a U-shaped valley like Yosemite in California, or Lauterbrunnen in Switzerland, is to feel a sense of monumental space and light. The openness is a direct gift of the ice. The glacier, in its slow, patient passage, cleared away the clutter, carved out the amphitheatre, and left behind a landscape of sheer grandeur. It is a landscape that speaks not of quick flowing water, but of immense, purposeful force. The U-shaped valley is the glacier's masterpiece, its enduring legacy written in stone long after the ice itself has vanished. It is the mold from which the river of ice has been lifted, leaving an empty, majestic cast for us to walk through today. The grand, sweeping form of a U-shaped valley is the glacier's masterpiece on a colossal scale, a work of art meant to be taken in from a distance. But to understand the true intimacy of the glacier's power, to comprehend the minute-by-minute, grain-by-grain mechanics of its erosion, one must look closer, much closer. On the polished surfaces of bedrock that once lay beneath the ice, the glacier has left behind a delicate, intricate script, a record of its passage etched not in ink, but in stone. These are the striations and grooves, the fine-line drawings of the ice's relentless touch. After a glacier retreats, it often unveils vast pavements of smoothed and polished bedrock. These surfaces, known as glacial polish, feel surprisingly smooth to the hand. their roughness ground away by an abrasive force as fine as any sandpaper. Upon this polished canvas, the most common inscriptions are striations. These are thin, parallel scratches, often just a few millimeters deep and wide, running in long, unbroken lines across the rock. They look as if a giant took a sharp nail and dragged it with immense, consistent pressure across the stone, and in a sense that is precisely what happened. The tool that created these scratches was not a single object, but a multitude of them. Embedded within the soul of the moving glacier were countless rock fragments, pieces of granite, shards of basalt, chunks of quartz, all trapped in the ice. These fragments, held fast by the immense pressure of the overlying ice, became the glacier's chisels and gravers. As the glacier inched forward, these tools were dragged across the underlying bedrock. A fragment of quartz, harder than the surrounding granite or limestone, would cut a fine line. A smaller, sharper stone would produce a finer scratch. A larger, more angular one might gouge a deeper groove. The unidirectional, relentless nature of the ice's flow ensured these lines were straight and parallel, a perfect record of the glacier's direction of travel. These markings are more than just scars. They are a diagnostic tool for geologists. By mapping the orientation of striations across a landscape, one can reconstruct the precise flow path of long-vanished ice sheets. They tell a story not just of movement, but of consistency. The straightness of the lines indicates a steady, unimpeded flow. When the striations suddenly shift direction or become chaotic, it signals that the ice encountered an obstacle, its path diverted, or its base becoming tangled. But striations are the fine brushwork. Alongside them, one often finds grooves. These are the same phenomenon on a much larger scale. Instead of a nail being dragged, imagine a log or a massive boulder. Grooves are channels that can be centimeters, even decimeters deep, carved out by particularly large and durable rocks that were dragged beneath the ice for great distances. They are the grand canals of glacial erosion, and walking along one is like walking in a rut, carved by a wheel of unimaginable size and weight. Some grooves are so large and well-defined they seem almost artificial, as if crafted by some ancient, purposeful hand. The very presence of these features reveals the specific conditions at the glacier's base. Glacial polish and fine striations indicate a phenomenon known as abrasion was dominant. This requires a hard bed, smooth, coherent bedrock, and a steady supply of fine, abrasive sediment at the ice-rock interface. It is the glacier's finesse work. Conversely, the presence of deep, chaotic gouges and a lack of polish suggests plucking was the primary force, where the glacier was tearing rock fragments away from a more fractured and uneven bed. There is a profound intimacy in running your fingers over a glacial striation. The rock is cold and smooth. The line is perfectly straight. In that touch, you are connecting with a moment frozen in time. You are touching the path of a single stone, a pebble that was locked in ice hundreds of feet thick, pressed against this very spot with tons of force, and then dragged inexorably downhill for centuries. That pebble is long gone, washed away by meltwater, but its signature remains. It is a fossilized whisper of motion. These delicate lines are also tragically ephemeral. They are the first features to vanish after the ice retreats. A few decades of wind, rain, and frost weathering are enough to blur them. Lichens colonize the polished surfaces, their acidic secretions slowly breaking down the rock and erasing the fine scratches. The most pristine striations are found only in recently deglaciated landscapes. Their fleeting beauty a reminder that the glacier's most subtle artwork is also its most fragile. So, while we marvel at the vast U-shaped valleys and the towering cirques, let us not forget the miniature scriptures left behind. The striations and grooves are the fundamental language of glacial erosion. They are the evidence of the countless individual interactions between ice and stone that, when multiplied by millions of years and trillions of rocks, result in the reshaping of continents. They remind us that the grandest of sculptures begin with the smallest of strokes. The glacier, in its patient, grinding journey, was both a grand architect and a meticulous engraver, leaving its signature on the land in lines both monumental and minute. High on the flanks of mountains, in the realm of thin air and relentless wind, lies some of the most dramatic and evocative landscapes shaped by ice. The cirques, these vast amphitheatre-like hollows with their steep, sheer headwalls and often containing a small, jewel-like tarn lake, are not merely accidental depressions. They are the cradles of glaciers, the very spots where these rivers of ice are born and where they exert their first, most focused power upon the mountain. A cirque is a bowl-shaped basin carved into the mountain, a monumental scoop taken out of the rock, and its formation is a story of slow, persistent attack by snow and ice on the highest and most vulnerable parts of a peak. The process begins not with ice, but with a simple patch of snow. On a north-facing slope or in a sheltered depression where the summer sun's rays are weak, a seasonal snowbank persists long after the surrounding snow has melted. This is the seed. Year after year, this snowbank survives, its presence slowly altering the very rock beneath it. The critical agent here is the freeze-thaw cycle. Meltwater from the daytime sun seeps into cracks and joints in the rock surrounding the snowbank. At night, when temperatures plummet, this water freezes. As it turns to ice, it expands with tremendous force, acting like a wedge, prying apart the rock and enlarging the cracks. This process, called frost shattering or gelifraction, slowly but surely quarries away fragments of rock, causing the back wall of the depression to steepen and retreat. Over centuries, this initial hollow deepens enough for the seasonal snowbank to become permanent. It evolves into a fern field, a basin of granular, compacting snow that survives year-round. The weight of this accumulating snow and fern now begins to exert its own influence. It starts to flow ever so slowly outward and downward. This nascent glacier, often called a cirque glacier, now begins to act as a more efficient erosive tool. The real sculpting begins. The glacier employs its two primary methods here with devastating effect. At the base of the steep headwall, a fascinating process called bergschrund erosion takes place. A bergschrund is a special type of crevasse that forms where the moving glacier pulls away from the stationary ice and snow attached to the headwall. This deep crack allows meltwater to penetrate to the bedrock at the very base of the cliff. Here, the freeze-thaw cycle is amplified, violently plucking rocks from the cliff face. Simultaneously, the rock fragments already embedded in the glacier's base act like sandpaper, abrading and polishing the floor of the cirque, deepening it further. The combination of these forces, frost, shattering on the headwall and glacial abrasion on the floor, works in a vicious cycle. As the glacier deepens the basin, it creates an even steeper, taller headwall, which is then more exposed to frost shattering. This shattered rock falls onto the glacier below, providing it with more abrasive tools to deepen the basin further. The cirque essentially digs its own grave, growing deeper and larger with each passing millennium. The glacier acts as a conveyor belt, constantly removing the debris quarried from the headwall, ensuring the process never stalls. The classic, armchair-shaped form of a cirque is a direct result of this focused erosion. The sides of the amphitheatre become steep and enclosing because the glacial erosion is most intense at the centre of the basin, where the ice is thickest and the flow is most concentrated. The characteristic lip at the downhill edge of a cirque is formed because the glacial erosion suddenly decreases at the point where the ice begins to flow out of the confining basin and into the main valley, leaving a rock threshold. Often, when the glacier finally melts away, the cirque it leaves behind contains a deep, often circular lake known as a tarn. This lake forms because the glacial erosion has scooped out a basin deep enough to intercept the water table, or because the lip of the cirque acts as a dam, trapping meltwater and rainfall. These tarns, with their dark, cold waters reflecting the sheer cliffs above, are among the most serene and beautiful features in the mountains, a quiet remnant of the powerful ice that once resided there. When two or more cirques form on different sides of the same mountain, they begin to carve away at its very heart. Their headwalls retreat toward each other, sharpening the summit into a steep, pyramid-like peak known as a horn. The most famous example is the Matterhorn in the Alps, a mountain whose dramatic form is entirely the product of cirque erosion. Similarly, the knife-edge ridges known as arêtes are formed when two parallel cirques erode the ridge between them to a narrow, serrated edge. To stand at the edge of a cirque is to stand at a place of origins. The silence here is profound, broken only by the wind and the occasional trickle of meltwater. One can almost feel the absence of the ice that once filled this vast bowl. The cirque is a negative space, a mold created by the presence of its frozen sculptor. It is the glacier's first and most personal signature on the mountain, a testament to how a small, persistent patch of snow can, given enough time, carve a hollow so large and so dramatic that it defines the entire character of the peak. It is the birthplace of ice and the engine of mountain sculpture. There are places on Earth where the mountains do not merely slope down to the sea, they plunge. Sheer cliffs of dark rock, often shrouded in mist, rise directly from deep, silent, and impossibly blue waters. These are not river valleys flooded by the ocean. These are fjords. They are the most dramatic and conclusive evidence of a glacier's power. The final chapter in the journey of a river of ice, where it meets the vastness of the sea and carves a landscape of sublime, almost forbidding grandeur. A fjord is a U-shaped valley, but one that was carved so deeply with such immense force that the ocean itself was invited to fill the void left behind by the vanished ice. The story of a fjord begins high in the mountains, with a glacier that has grown to a monumental size. This is not a small cirque glacier, but a major valley glacier, or even an outlet glacier, flowing from a massive ice sheet. As this river of ice flows downhill, it does not merely scrape and widen its valley. It focuses a terrifying amount of energy on deepening it. The glacier's immense weight and the abrasive debris trapped in its base act like a colossal grinding wheel. But there is a crucial difference here. At the glacier's terminus, where it meets the sea, the erosion becomes uniquely efficient. When a glacier flows into the ocean, its terminus becomes a tidewater glacier. Here, the ice does not simply melt away from the sun's warmth. Instead, it carves. Great blocks of ice crack off the face with a thunderous roar and crash into the water as icebergs. This process of carving is a rapid and powerful form of ablation. It constantly removes ice from the terminus, pulling the glacier forward, encouraging it to flow faster and extend farther out to sea. This dynamic, active front allows the glacier to continue its deep excavation even at sea level. The glacier effectively becomes a self-extending plough, digging its trench far below the surface of the water, often hundreds of meters deeper than the surrounding seafloor. This leads to the most defining characteristic of a fjord, its profound depth. While the water at the mouth of a fjord might be a few hundred meters deep, the seabed within the fjord itself often lies much deeper. This shallow threshold at the entrance is called the sill. The sill is composed of tough, resistant bedrock that the glacier could not erode as deeply, or of a terminal moraine, a pile of debris dumped by the glacier when it was at its maximum extent. Behind this sill, the fjord's true depth is revealed, a hidden underwater canyon that can reach depths of over 1,000 meters. The glacier, in its relentless advance, carved a valley that lies far below current sea level. The final act in the creation of a fjord is the glacier's retreat. As the global climate warmed at the end of the last ice age, the massive glaciers that filled these valleys began to melt back. Their tremendous weight, which had been pressing down on the continental crust, was lifted. The land began to slowly rebound, a process known as isostatic uplift. But the melting of the ice sheets also caused global sea levels to rise dramatically. In the race between the land rising and the sea won. The ocean poured into the deep, steep-sided valleys that the glaciers had vacated, creating the breathtaking seascapes we see today in places like Norway, New Zealand, Chile, and Alaska. The environment within a fjord is as unique as its geology. The shallow sill at its mouth restricts water circulation with the open ocean. This often creates a distinct layering of water, a surface layer of fresh. Cold meltwater from surrounding rivers and glaciers floats atop a deeper, denser, and saltier layer of seawater that has crept in over the sill. This stratification can create unique ecosystems. The deep, cold, and often dark waters of the main fjord basin can become oxygen depleted, preserving organic material in near-perfect condition for centuries. For humans, fjords have always been both sanctuary and challenge. Their calm, protected waters provide excellent harbours and fishing grounds, and their steep sides have historically made overland travel difficult, fostering isolated communities. To sail into a fjord is to embark on a journey into the very heart of the Ice Age. The water is a mirror reflecting cliffs that were polished by ice, and the silence is broken only by the cry of a seabird or the distant rumble of a rockfall from a slope that is still adjusting to the glacier's absence. A fjord, then, is more than a scenic wonder. It is the ghost of a glacier. It is the ultimate expression of glacial power, a monument to an ice sheet's ability to reach the sea and, in doing so, sculpt the coastline itself. It is a landscape that speaks of immense forces on a geological scale, of the weight of continents and the rise of oceans. To witness a fjord is to understand that the work of ice does not end at the shoreline. It merely changes form, leaving behind a drowned, silent valley that continues to tell its story to the waves. A glacier from a distance presents a facade of pristine whiteness, a pure river of ice flowing from the high peaks. But this purity is an illusion. A glacier is the most powerful landscape-shifting force on the planet, and like any great earth-moving project, it generates immense amounts of debris. It is not a clean sculptor, but a messy, relentless transporter, collecting, crushing, and carrying the pulverized evidence of its own destructive power. The material it leaves in its wake, the piles of rock and sediment that trace its path and mark its boundaries, forms the vocabulary of its history. This is the world of moraines and glacial till, the rubble of the Ice Age. The journey of this debris begins with the glacier's erosive tools, plucking and abrasion. As the ice grinds over the landscape, it quarries rocks of all sizes from the bedrock beneath it and from the valley walls that confine it. These fragments, from fine powder to house-sized boulders, become incorporated into the ice. Some are dragged along the base, sanding the bedrock further. Others are buried within the glacier's heart, and some ride along on its surface, having fallen from the surrounding cliffs onto the ice. This mixture of unsorted angular rock material is known as glacial till. Till is not like river sediment, which is sorted by water into layers of sand, gravel, and silt. Till is a chaotic jumble. A single deposit may contain fine clay, sharp sand, rounded pebbles, and jagged boulders all mixed together indiscriminately. This is the glacier's signature. It transports material with brute force, not with the discerning flow of water. As the glacier moves, it does not simply hide this debris within itself. It organizes it into long, linear ridges that pile up along its edges and at its terminus. These ridges are moraines, and they are the most visible monuments of a glacier's presence. They are the bulwarks of ice, the levees of rock that outline the glacier's body and chronicle its past advances and retreats. The most common moraines are the lateral moraines. These form as long parallel ridges running along the sides of a glacier, like railway embankments. They are composed of rock and soil that has fallen from the valley walls onto the edges of the ice or has been scraped from the sides of the valley by the glacier's flow. As the glacier moves, it carries this debris downhill and it accumulates along its margins. A hike along a valley once occupied by a glacier will often reveal these distinct ridges high on the valley's sides, marking the exact height the ice once reached. When two valley glaciers merge, their inside lateral moraines meet. Instead of stopping, they combine and are carried down the center of the new, larger glacier. This creates a medial moraine, a dark stripe of debris running along the glacier's surface like a highway line. A glacier with several tributaries can have multiple medial moraines, creating a striped effect that is clearly visible from the air, a map of its own confluence written in rock dust. But the most significant moraine is the terminal moraine, also called an end moraine. This is a massive arc-shaped ridge of till that marks the glacier's maximum advance. It is the dump pile of the ice. As the glacier flows, it acts like a colossal conveyor belt, carrying debris from the entire length of its valley toward its snout. At the terminus, where the ice finally melts, it drops all of this transported material in a gigantic pile. The terminal moraine is the glacier's stopping point, its furthest reach. It can form a formidable dam, often blocking the meltwater to create a lake behind it. If a glacier stabilizes for a period during its general retreat, it may pause long enough to deposit a new, smaller ridge of till. These are recessional moraines, and they lie behind the terminal moraine like a series of frozen waves, each one marking a standstill in the ice's long, slow withdrawal from the land. Beneath the glacier, another layer of debris is being laid down. This is ground moraine, a wide, rolling blanket of till that is deposited as the ice melts in place during retreat. It does not form a distinct ridge, but rather a vast, uneven plain of low hills and small depressions called knob and kettle topography. This is the sheet of rubble that the glacier leaves behind as its final gift to the landscape, the foundation for future soil and ecosystems. The story told by moraines and till is one of immense power and transience. The terminal moraine stands as a monument to a past victory of cold over warmth, a moment when the ice pushed its furthest. The lateral moraines are the ghostly impressions of the glacier's bulk. The chaotic, unsorted till is the raw material of new landscapes. These features are not sterile piles of rock. They are the fertile ground from which life slowly returns after the ice has departed. Forests eventually take root on the moraines, and lakes fill the kettles. The debris of the glacier's progress becomes the building blocks for the future, a testament to the fact that even in its retreat and dissolution, the ice continues to shape the world. It is a cycle of destruction and creation, written in the language of stone and soil. Amid the orderly patterns of a landscape, the layered bedrock, the consistent soil types, the local stones that match the underlying geology, there sometimes appears a solitary anomaly, a massive boulder composed of a rock type found nowhere in the immediate vicinity rests impossibly on a hilltop, in a field, or in the midst of a forest. It is too large to have been moved by human hands, its composition alien to its surroundings. This is a glacial erratic, more than just a rock. It is a wanderer, a silent voyager from a distant land, and its presence is one of the most personal and puzzling pieces of evidence left behind by the ice. The word erratic comes from the Latin, meaning to wander, and it is a perfectly apt name. These stones are the orphans of the Ice Age, displaced from their parent bedrock and dropped in a foreign land. Their journey began when the advancing ice sheet, often thousands of feet thick, encountered an outcrop of resistant rock. Through the relentless process of plucking, meltwater would seep into fractures, freeze, and expand, prying loose large blocks. These blocks, some as large as houses, were then engulfed by the glacier. They became frozen into the ice, passengers on a slow-moving conveyor belt that cared nothing for their size or weight. There are two primary ways an erratic travels. The most common is embedded within the glacier itself, dragged along at its base, where it acted as a cutting tool, gouging deep striations into the bedrock below. Others, perhaps falling onto the surface from a protruding cliff, would ride on top of the ice, a king on a frozen throne, surveying a world of white. These surface riders travelled relatively cleanly, while those at the base were ground against the floor, their edges chipped and rounded, their surfaces often polished and striated themselves, bearing the scars of their long and abrasive journey. The significance of the erratic lies not just in its journey, but in its origin. The type of rock tells a story. A granite boulder sitting on a limestone plain is a clear signpost pointing back to its source. By identifying the unique mineral composition of an erratic, geologists can trace a path back to its parent bedrock, sometimes hundreds of miles away. In doing so, they can map the precise flow direction of ancient ice sheets. These stones are the breadcrumbs left by the retreating ice, allowing us to reconstruct its former paths with remarkable accuracy. The famous Madison boulder in New Hampshire, a mass of granite weighing over 5,000 tons, was carried by ice from a source area many miles to the north. It is a monumental mile marker on a frozen highway. Beyond their scientific value, erratics have long held a powerful place in the human imagination. In the centuries before the theory of glaciation was accepted, their presence was a profound mystery. How did a massive boulder come to rest on a completely different type of rock? Early explanations ranged from the biblically cataclysmic, the Great Flood, to the fanciful, such as giants hurling stones at one another. Their strange, solitary presence made them natural landmarks, meeting points, and objects of veneration. Many erratics became sacred sites, altars for rituals, or subjects of legend. They were seen as tokens from the gods dropped from the sky or left by mythical beings. There is a particular magic to encountering an erratic. In a cultivated field, it is the one thing the farmer could not move, working around it for generations. In a modern park, it becomes a climbing rock for children, its true history unknown to them. To place a hand on its cool, weathered surface is to touch a piece of a distant mountain. It is to connect with an event of immense scale and power, the slow, crushing passage of a continent of ice. The erratic is a relic of that time, a stoic witness that has survived the thaw, a piece of the puzzle that helped humanity unlock the secret of the ice ages. The erratic's final resting place is as telling as its composition. An erratic perched precariously on a pinnacle of different rock illustrates the concept of ice melting in place. The glacier, thick enough to bury the entire landscape, simply melted down around the boulder, depositing it gently on the spot where it was last held. It did not roll or fall into place. It was lowered, as if by a retreating crane. These wanderers of stone are more than just geological curiosities. They are monuments to impermanence and power. They demonstrate that the very continents are not fixed. Their pieces can be shuffled by the slow hand of ice. An erratic is a symbol of displacement, a reminder that the world has been rearranged on a grand scale, and that the most solid and permanent-looking objects can be travelers from a forgotten age. They sit in our fields and forests, quiet and heavy with stories, waiting for someone to ask the simple question, "How did you get here?" The answer is an epic poem of ice, time, and the restless nature of the earth itself. A glacier may appear as a solid, frozen monolith, a creature of absolute stillness. But within its icy heart there is a secret flowing life. It is laced with a circulatory system of water, a network of sapphire veins and milky arteries that pulse with the rhythm of the sun and the seasons. This hidden hydrology is what animates the ice, what carves it from within, and what ultimately connects it to the world beyond its frozen borders. The glacier is not a dry desert of ice. It is a reservoir, a filter, and a conduit alive with liquid motion. The water's journey begins on the surface. Under the summer sun, the glacier's skin awakens. Snow melts into rivulets that trace delicate paths across the white expanse. These streams gather into larger channels, flowing in S-shaped curves that mirror great terrestrial rivers, but carved into ice instead of soil. Their water is crystal clear, cold, and incredibly pure. But this surface world is ephemeral. As these streams flow, they often encounter a crevasse or a moulin. A moulin, from the French word for mill, is one of the most dramatic features of a glacier's hydrology. It is a vertical or near-vertical shaft that acts as a drain pipe, swallowing a surface river whole. The water plunges into the depths with a thunderous roar, disappearing into the blue darkness. These shafts can extend hundreds of feet down to the very base of the glacier. The formation of a moulin is often a point of no return for the surface water, a plunge into the glacier's hidden underworld. Once at the bed, the water enters a realm of immense pressure and mystery. It flows in thin films and through interconnected tunnels at the interface between the ice and the bedrock. This subglacial plumbing system is constantly changing, shaped by the water's own pressure and the shifting ice above. This water at the base is crucial, as it lubricates the glacier's bed, facilitating basal sliding, the very process that allows the ice to flow more rapidly. The pulse of meltwater in summer increases this lubrication, causing the entire glacier to speed up in its journey downhill, a seasonal heartbeat driven by hydrology. Eventually, this water must emerge. It often gushes out from beneath the glacier's terminus in a powerful, ice-cold stream, but it is no longer the clear, pristine liquid that entered the moulins. Now it is glacial milk. This term perfectly describes its opaque, milky turquoise appearance. The color comes from rock flour, finely ground bedrock, the literal dust of the glacier's grinding power. As the ice scrapes over the bedrock, it pulverizes the rock into particles so fine they are like flour. These minuscule sediment particles are suspended in the meltwater. When the light hits them, they scatter the blue and green wavelengths, giving the water its distinctive, ethereal hue. This rock flour is the glacier's signature, its message to the lowlands. The rivers that flow from glaciers are some of the most sediment-rich in the world. They are liquid conveyor belts carrying the mineral wealth of the mountains downstream. This sediment will eventually settle in quieter waters, building fertile floodplains and deltas. The land is being nourished by the very bones of the mountains, ground down by the ice and delivered by the water. The water within a glacier is also a sculptor of its interior. The flow of water, both on the surface and within, carves intricate channels and caverns, creating a hidden landscape of blue grottos and underground rivers. This internal melting can significantly weaken the ice's structure, contributing to its dynamic evolution. The stunning blue color seen in crevasse walls and ice caves is a result of this very purity and density. The ice absorbs all other colors of the spectrum, scattering only the blue light back to our eyes. The interplay of blue veins and glacial milk represents the complete cycle of the glacier's interaction with the Earth. The clear blue water is the agent of internal change and lubrication, while the milky water is the carrier of its erosional legacy. One represents the glacier's present dynamics, the other the evidence of its past power. To witness the emergence of a subglacial stream is to see the glacier giving birth to a river. It is a powerful elemental process. The water that emerges has been on a long and transformative journey, from the freedom of the sunlit surface, through the pressurized darkness at the bed, and back into the light, now charged with the mineral essence of the mountain. This water is the lifeblood of downstream ecosystems and human civilizations. It is the final, vital connection between the silent, high world of ice and the vibrant, flowing world of the valleys. The glacier does not simply hold water, it breathes it. And with every summer sun, it exhales these rivers of milk and blue, feeding the world below. The story of individual glaciers, of cirques and U-shaped valleys, is but a single paragraph in a much longer, more profound epic. To truly understand the scale of ice's power, we must step back, far back, in time. We must envision a world not just with glaciers in its mountains, but a world dominated by ice. A planet where the familiar outlines of continents were obscured, where sea levels plummeted, and where the very air grew thick with dust from barren, frozen plains. This was the Pleistocene epoch, the Great Ice Age, a time when the Earth's thermostat swung wildly and the cold repeatedly gripped the planet in a frozen embrace. The concept of past ice ages is a relatively young one in human thought. For centuries, the erratics and striations we've discussed were geological puzzles without a solution. It was only in the 19th century that scientists like Louis Agassiz began to piece together the evidence, proposing the then radical idea that vast sheets of ice had once covered Europe and North America. The evidence was overwhelming and globally consistent. Giant U-shaped valleys far from any existing glacier, polished bedrock plains stretching for hundreds of miles, and those mysterious out-of-place boulders. The only logical conclusion was that the climate of the entire planet had undergone dramatic shifts. The engine of these great freezes lies not in the Earth itself, but in the subtle, rhythmic changes in our planet's journey around the Sun. These are the Milankovitch cycles, named after the Serbian scientist who calculated their effects. There is no single ice age cycle, but rather a complex interplay of three astronomical rhythms. The first is the change in the eccentricity of Earth's orbit, a 100,000-year cycle where our planet's path around the Sun shifts from more circular to more elliptical, changing the total solar energy received. The second is the tilt of Earth's axis, which varies over about 41,000 years, affecting the intensity of the seasons. The third is precession, a 26,000-year wobble of the axis, like a spinning top winding down, which determines whether Northern Hemisphere summers occur when Earth is closest to or farthest from the Sun. Alone, each of these cycles has a modest effect. But when they align to minimize summer sunlight in the high northern latitudes, where most of the planet's landmass is located, a threshold is crossed. A critical amount of winter snow fails to melt during the brief summer. It begins to accumulate year after year, century after century. The growing ice sheets, with their brilliant white surfaces, reflect more of the sun's energy back into space, a process known as the albedo effect. This creates a powerful positive feedback loop. More ice leads to more cooling, which leads to more ice. The planet tips into a glacial period. The world during a glacial maximum was almost unrecognizable. At their peak, ice sheets over 2 miles thick smothered much of North America, reaching as far south as New York City and Seattle. A similar sheet covered northern Europe, spanning from the British Isles to Siberia. So much water was locked up on land that global sea levels dropped by over 120 meters, nearly 400 feet. Coastlines extended far beyond their present margins. Continents grew. Alaska was connected to Siberia by the Bering Land Bridge, a vast, cold, dry plain known as Beringia. The climate everywhere was colder and drier. Deserts expanded and forests gave way to grasslands and tundra. This was not a single, simple event. The Pleistocene was a roller coaster of climate. Over the last 2.6 million years, there have been over 50 glacial cycles. Long, brutal glacial periods, each lasting tens of thousands of years, were separated by shorter, warmer intervals like the one we live in now, called interglacials. Our own Holocene epoch, which began about 11,700 years ago, is one of these warm respites. The ice retreated, the sea levels rose, and the planet we know today took shape. The legacy of these ice ages is etched into the modern world. The Great Lakes of North America are basins scoured and dammed by the ice. The fertile soils of the American Midwest are composed of glacial till and wind-blown loess. The fjords of Norway and New Zealand are drowned glacial valleys. The very distribution of species, including our own human ancestors, was shaped by the advancing and retreating ice, which opened and closed migration routes across the globe. To contemplate the ice ages is to understand the profound dynamism of Earth's climate. The conditions we consider normal are, in the long view, an exception. The stable world that allowed human civilization to flourish is a fleeting moment of warmth in a much colder history. The glaciers we see today, in the Alps or the Rockies, are the shrunken, scattered descendants of continental giants. They are reminders of a time when the world froze, when ice was the dominant force on the planet, and when the rhythm of the Earth was not set by the quick turning of seasons, but by the slow, majestic beat of astronomical cycles. They remind us that change is the only constant, and that the cold, silent power of ice is never far from the surface of our world. To the human eye, a glacier presents a landscape of absolute purity and sterility. A vast expanse of white and blue, it seems a place where life could not possibly gain a foothold. It is a world of extreme cold, shifting surfaces, and a stark absence of soil. But this impression of barrenness is a profound illusion. Glaciers are not frozen deserts. They are environments in their own right, home to a unique and resilient collection of life forms that have adapted to thrive in this seemingly hostile realm. This is the world of extremophiles, organisms that have turned the ice itself into a habitat, creating an unseen ecosystem that pulses with activity just beneath the surface. The foundation of this icy food web is not the sun's energy captured by plants, as in most ecosystems, but by the power of dust. The key ingredient is cryoconite. This dark, fine-grained dust, a mixture of wind-blown silt, soot, and microscopic organisms, is the lifeblood of the glacial world. When this dark material lands on the ice, it absorbs solar radiation, causing it to melt down into the surface, forming small, water-filled holes known as cryoconite holes. These holes are miniature, self-contained worlds. Each one is a microcosm, a liquid oasis in a solid desert. The cryoconite at the bottom of the hole is not just inert dust. It is a rich microbial mat teeming with life. Photosynthetic cyanobacteria are the primary producers here. They capture the sun's energy, even through a thin layer of ice, and use it to fix carbon dioxide, creating organic matter. They are the plants of the glacier. Alongside them live heterotrophic bacteria, algae, and even tiny animals like tardigrades, microscopic water bears, famous for their incredible resilience. These cryoconite holes can coalesce, forming extensive, dark patches on the ice that accelerate melting and create a complex, interconnected aquatic network on the glacier's surface. Venturing beyond these microhabitats, larger, more specialized creatures emerge. In the coastal glaciers of Alaska and the Pacific Northwest, the summit of the ice can become a temporary refuge for predators. The snow spider, Pardosa glacialis, stalks its prey across the snowfields, its dark body absorbing just enough warmth to remain active. But the most iconic, larger resident of the glacial surface is the ice worm, Mesenchytreus solifugus. These small, black, thread-like annelids are true wonders of adaptation. They are the only known worm that completes its entire life cycle in glacial ice. They remain dormant during the day, buried deep in the ice to avoid the sun and predators. At night, and on overcast days, they swarm to the surface to feed on algae and pollen. They possess specific proteins that prevent their cells from freezing, allowing them to move through a maze of ice crystals at temperatures that would be fatal to almost any other organism. Even the color of a glacier can betray the presence of life. Red snow, or watermelon snow, is a striking phenomenon caused by blooms of a unique type of green algae, Chlamydomonas nivalis. This algae is normally green, but it produces a bright red carotenoid pigment as a natural sunscreen to protect itself from intense ultraviolet radiation at high altitudes. This crimson hue darkens the snow surface, absorbing more heat and accelerating melting. a small but significant example of life directly influencing its physical environment. Beneath the glacier, in the dark, high-pressure world of the subglacial bed, another ecosystem may exist. Here, in total darkness, life cannot rely on the sun. Instead, it must be chemosynthetic, drawing energy not from light, but from chemical reactions within the bedrock itself. Minerals like pyrite and sulfides can be oxidized by specialized bacteria, providing the foundational energy for a food web that is completely isolated from the world above. While this deep, dark biosphere is difficult to study, its potential existence suggests that life can persist even under the immense weight of a continent of ice, hinting at the possibility of life in similar extreme environments on other worlds, like the icy moons of Jupiter and Saturn. The life of the glacier is fragile. These ecosystems are finely tuned to the specific conditions of cold, light, and meltwater. As glaciers retreat and vanish at an accelerating pace, these specialized habitats are disappearing before we have even fully understood them. The ice worm, the snow algae, the entire cryoconite community, they have nowhere else to go. Their world is literally melting away. To know that a glacier is alive is to see it in a new light. It is not a sterile, abiotic sculpture. It is a living skin on the earth, a membrane teeming with microbial cities, prowled by tiny predators and colored by algal blooms. The meltwater that flows from the glacier's snout is not just water. It is rich with these microscopic organisms and nutrients, seeding the downstream rivers and soils with life. The glacier, therefore, is not an endpoint but a source. It is a nursery for resilience, a testament to life's astonishing ability to find a way in the coldest, hardest places. The next time you look upon a river of ice, remember that you are not just looking at frozen water. You are looking at a habitat, a biome, a world within a world, quietly thriving in the deep freeze. High in the thin, cold air of the world's mountain ranges, a silent, slow-motion hydrological miracle takes place. Glaciers function as the planet's most strategic water reservoirs, a critical resource for nearly 2 billion people. They are not static ice. They are dynamic, climate-driven storage systems that perform a vital function. They hold winter's precipitation and release it gradually throughout the summer. This simple, elegant timing is what makes them indispensable to the vast river systems that support agriculture, cities, and ecosystems across the globe. They are the world's water towers, and their steady melt is the pulse that sustains life during the driest months. The mechanism is one of perfect natural engineering. In the high mountains, precipitation falls mainly as snow during the long winter. If this snow were to melt immediately in the spring, it would cause catastrophic flooding, rushing downstream in a short, uncontrollable surge, and then leaving the rivers parched for the rest of the year. The glaciers interrupt this cycle. They capture this snow, storing it as ice for years, decades, or even centuries. Then, as the warm, dry summer air arrives, the glacier begins to melt at a relatively steady, predictable rate. This meltwater feeds the headwaters of rivers, ensuring a consistent, reliable flow precisely when it is needed most. During the growing season, when rainfall is often scarce, this regulating function is what hydrologists call stream flow regulation. A glacier-fed river has a very different personality from a rain-fed one. Its flow is more stable, its floods less flashy, and its late summer levels far higher. For regions like the Andes, the Himalayas, and the Rockies, this glacial subsidy is not a luxury. It is the foundation of water security. The mighty rivers that spring from these ranges, the Ganges, Indus, Yangtze, and Colorado, are, to a significant degree, creations of the ice that crowns their headwaters. The water that irrigates the fields of Pakistan, that powers the cities of northern India, that quenches the thirst of millions in arid regions, fell as snow on high glaciers long before it began its journey to the tap. The concept of the peak water point is crucial to understanding the current crisis. For any given glacier, there is a tipping point in its relationship with a warming climate. Initially, as temperatures rise, melting accelerates. For a time, this can actually increase the summer runoff from the glacier, providing a surplus of water. This is the period of peak water. But it is a temporary and ultimately deceptive bounty. It is like drawing down the principle of a savings account. Once the glacier has retreated beyond a certain point, once its volume has shrunk too far, the annual melt will begin to decline. The reservoir is being emptied. The surplus turns to deficit. We are now witnessing this transition across the globe. Glaciers in the Andes have already passed their peak water, threatening the water supply for cities like La Paz and Lima. In the Himalayas, the timing of peak water is a subject of intense study and profound concern for the nations downstream. When the glacial buffer disappears, these great rivers will become far more dependent on seasonal monsoon rains, making them volatile, unpredictable, and prone to devastating droughts. The slow, reliable release of the ice will be replaced by the feast or famine cycle of precipitation. The loss of these frozen reservoirs also has a direct impact on water quality. Glacial meltwater is naturally cold and rich in minerals, conditions that many aquatic species are adapted to. As the contribution of glacial melt decreases, river temperatures rise and sediment loads change, disrupting fragile aquatic ecosystems. The very character of the river changes from a cold, milky turquoise thread from the mountains to a warmer, clearer, and ultimately a shallower stream. The role of the glacier as a water tower is a profound example of the interconnectedness of the Earth's systems. The health of a distant, seemingly remote ice field is directly linked to the food security and political stability of populations thousands of miles away. The slow decay of these ice reservoirs is not just an environmental indicator, it is a direct threat to a hydrological rhythm that civilizations have depended upon for millennia. To stand at the terminus of a glacier and watch the milky water pour forth is to witness the opening of a tap. That flow is a measure of the glacier's health, a real-time reading of the balance between accumulation and ablation. For now, the tap is still running, but the flow is becoming more erratic, a symptom of a system under stress. The great water towers of the world are being dismantled, their stored wealth spent in a geological instant. The silent retreat of the ice is, in reality, a very loud alarm, warning of a future where the steady, life-giving pulse of meltwater may fade into a memory, leaving only the uncertainty of the rain. There is a sound in the polar realms that defines the interface between ice and ocean, a sound that is neither wave nor wind. It is a deep, low-frequency groan, a sharp crack, like a cannon shot, and finally, a thunderous rolling roar that echoes off the fjord walls.
This is the sound of birth at the calving front.
It is here, where the largest glaciers meet the sea, that ice completes its long terrestrial journey and is reborn into the aquatic world as icebergs. This process, calving, is one of the most dynamic and spectacular events on Earth, a dramatic release of energy that marks the glacier's final surrender to the warmth it has resisted for centuries. A calving glacier, known as a tidewater glacier, is a river of ice flowing into a marine embayment. Its end is not a quiet melting margin, but a towering vertical cliff of ice that can soar hundreds of feet above the waterline and extend even deeper below it. This ice cliff is the front line of a battle between the immense forward momentum of the glacier and the destabilizing influence of the water. The ocean is both a cradle and an executioner. It buoys the ice, attacks its foundation, and ultimately breaks it apart. The mechanics of calving begin out of sight. Seawater, which is typically a few degrees above freezing, relentlessly melts the submerged portion of the ice cliff, undercutting it and creating a deep notch. This process, called submarine melting, weakens the glacier's support structure. At the same time, the natural flow of the glacier continues to push the ice seaward. Crevasses propagated by the stretching of the ice as it floats deepen and intersect. The ice is being attacked from below by water and from within by its own stresses. It is only a matter of time before a section, weakened beyond its structural integrity, breaks free. The style of carving varies with the glacier's character. Sometimes it is a slow, graceful process. A large block, perhaps the size of a city building, will slowly lean forward, separating from the main cliff with a prolonged, grinding groan before plunging into the water in a movement of colossal, balletic grace. This is tabular carving, often seen from the vast ice shelves of Antarctica, producing flat-topped, monumental icebergs. More often, the process is violent and explosive. Serac collapse occurs when towering pinnacles of ice, already unstable from intersecting crevasses, topple without warning. The impact with the water is catastrophic, sending massive plumes of spray hundreds of feet into the air and generating powerful waves that radiate outward. The new iceberg, now liberated, rolls and bobs in the churning water, seeking equilibrium. It is a breathtaking display of raw power, a reminder that the glacier, for all its seeming permanence, is fragile at its edges. The newborn icebergs begin their own silent journeys. Driven by winds and currents, they become nomadic islands of fresh water. Their size dictates their fate. The largest, known as tabular icebergs, can be larger than some countries, platforms of ice so vast they are given names and tracked by satellites. As they drift into warmer waters, they begin to melt, sculpted by the sea into arches, caves, and fantastical shapes. They also perform a vital ecological function. The rock flour and nutrients trapped within the ice are released into the ocean as they melt, fertilizing the surface waters and triggering blooms of phytoplankton that form the base of the marine food web. Seals use them as resting platforms. Birds nest on them. They become temporary, floating oases of life. But the carving front is also a sensitive indicator of a glacier's health. The carving rate, the speed at which ice is lost, is a critical factor in the glacier's mass balance. In a stable state, the glacier flows to the coast, carves off icebergs at a steady rate, and its terminus remains in roughly the same position. However, when warming ocean waters increase submarine melting, the carving rate can accelerate dramatically. The front can undergo rapid, catastrophic retreat, sometimes losing miles of ice in a few years. The glacier's grounding line, the point where it loses contact with the seabed and begins to float, retreats inland, allowing even more ice to flow seaward, a positive feedback loop of disintegration. This is what is happening to many glaciers in Greenland and West Antarctica, where the birth of icebergs has become a symptom of a feverish climate. To witness a major carving event is to feel the Earth's pulse. The sound is visceral, a shock wave that is felt in the chest as much as heard by the ears. The sight of 1 billion tons of ice crashing into the sea is a humbling spectacle of nature's force. It is a moment of both creation and destruction. The glacier is diminished, but the iceberg is born, embarking on a final, melancholic voyage to melt away into the very seas that created it. The carving front is a theatre of constant change, where the patient journey of the ice culminates in a sudden, spectacular, and roaring finale. There is a library on this earth whose books are written not in ink, but in ice. Its pages are not turned by hand, but by the patient, layered accumulation of centuries. Its stories are not of kings and empires, but of the very air our ancestors breathed, of the storms that raged before the dawn of civilization, and of the delicate balance of our planet's climate. This library is the ancient ice of glaciers and ice sheets, and the method of reading it is the science of ice core drilling. To extract a cylinder of ice from a mile deep in the Greenland or Antarctic ice sheet is to open a time capsule, to pull a frozen straw from the earth that contains an uninterrupted, year-by-year diary of the past. The process begins in the planet's coldest, most pristine places. Teams of scientists establish camps on the vast, silent domes of ice in Greenland and Antarctica. Using a specialized drill, they begin to bore down, retrieving long cylindrical cores of ice, typically about 4 inches in diameter. Each section, carefully labeled and packed for shipment to laboratories around the world, is a slice of time. The deepest ice ever retrieved comes from over 3 kilometers down, capturing a record that stretches back nearly 1.5 million years in Antarctica. The fundamental principle is simple. Each year's snowfall is buried by the next, preserving a unique layer. Like the rings of a tree, these layers can be counted. In a single core, scientists can identify individual years, even individual seasons. A winter snowfall with its fine, powdery crystals looks different under the microscope from a denser, summer layer. By counting these annual layers, a precise chronology is built, a calendar frozen in ice. But the true magic lies not in the ice itself, but in the tiny, trapped bubbles. As the snow compacts into firn and then into solid ice, air pockets become sealed off from the atmosphere. These bubbles are literal samples of the ancient air. They are tiny, perfectly preserved samples of the Earth's atmosphere from the time they were trapped. By cracking these bubbles open in a vacuum chamber, scientists can analyze the chemical composition of the air from thousands of years ago. They can measure the concentration of greenhouse gases like carbon dioxide and methane with astonishing precision. The data from these ice cores has rewritten our understanding of Earth's climate history. They have revealed the dramatic rhythm of the ice ages. The cores show that over the last 1 million years, the climate has not been stable. It has oscillated between long, cold glacial periods and shorter, warmer interglacials, like the one we live in now. The graph of temperature and CO2 derived from the ice tells a powerful, synchronized story. When temperatures drop, CO2 levels drop. When temperatures rise, CO2 rises. The correlation is unmistakable, revealing the intimate link between greenhouse gases and global temperature. Furthermore, the ice contains a record of past events. A large volcanic eruption anywhere on the globe will spew sulfate aerosols into the stratosphere. These aerosols eventually fall to Earth, leaving a thin, acidic layer in the ice sheets that can be dated precisely. The ice has recorded the dust from ancient droughts, the lead pollution from the Roman smelters, and the soot from the Industrial Revolution. It is a ledger of both natural phenomena and human activity. One of the most profound discoveries came from comparing the ice core record with modern measurements. For the last 800,000 years, the concentration of CO2 in the atmosphere has never exceeded 300 parts per million. It oscillated between about 180 ppm during ice ages and 280-300 ppm during warm interglacials. Then the ice core record meets the instrumental record. The line on the graph, which had gently undulated for millennia, suddenly turns vertical. In little over a century, the CO2 concentration has skyrocketed to over 420 parts per million, a level the Earth has not experienced for millions of years. The frozen archive provides the critical context, showing just how radical and unprecedented our current human-driven experiment with the atmosphere truly is. To hold a piece of ice that fell as snow during the life of a Roman emperor, or when woolly mammoths still walked the earth, is a humbling experience. Within that clear, cold substance is a captured moment in time. The ice core is a time machine. It allows us to witness the planet's heartbeat, to see its regular rhythms, and to understand the profound shock we are now administering to its system. The glaciers are not just silent rivers, they are silent historians. They have been recording everything patiently, meticulously. And now, as we learn to read their frozen language, they are telling us a story of a stable past and a deeply uncertain future. They are the memory of the Earth, and we are only just beginning to understand the urgency of its message. The great rivers of ice are flowing backwards, not in their motion, for they still creep downhill under the force of gravity, but in their extent. They are shrinking, receding, withdrawing from the world. Across the globe, from the high Andes to the European Alps, from the Rockies to the mighty Himalayas, the story is the same, an era of retreat. The signal is unambiguous, the evidence etched into the landscape itself. The Great Melt is not a future prediction, it is a present-tense reality, a slow-motion vanishing act that is redrawing the world's mountainous maps. The most direct proof is written in the language of the land. A retreating glacier leaves a clear and recently exposed signature. Behind its current, often debris-covered terminus, lies a zone of raw, unvegetated ground. This land, known as the Forefield, is a stark testament to the ice's recent presence. The rock is freshly scoured, often bearing the telltale polish and striations we have come to recognize. But now these features are exposed to the air for the first time in thousands of years. Moraines that once marked the glacier's stable boundary now stand as empty ramparts, high and dry, far from the current ice edge. The most powerful evidence comes from repeat photography. A photograph of a glacier from the late 19th or early 20th century, placed beside one taken from the exact same vantage point today, tells a story of staggering loss. Where there was once a vast expanse of white ice filling a valley, there is now often only bare rock, a turquoise lake, and a shrunken, distant tongue of ice. The primary driver of this global retreat is the warming of the atmosphere. While complex factors like precipitation patterns play a role, the relentless rise in global temperatures has tipped the balance of the glacial mass budget decisively into the negative. The ablation zone, the area of melt, has expanded, reaching higher and higher elevations. The equilibrium line, the altitude where accumulation equals ablation, is climbing up the mountain slopes. Each summer, glaciers are losing more ice than they can regain in the winter. They are living off their capital, and that capital is finite. This melt is accelerated by powerful feedback loops. One of the most significant is the albedo effect. Pristine, white snow and ice are highly reflective, bouncing about 80–90% of solar radiation back into space. But as the glacier melts, it becomes dirtier. Darker morainal debris concentrates on the surface, and wind-blown dust and soot from industrial activity or wildfires settle on the ice. These dark surfaces absorb far more solar energy, accelerating the melting around them, which in turn exposes more dark ground, creating a self-reinforcing cycle of melt. The glacier, in effect, begins to melt from the inside out. The rate of retreat is not uniform. It depends on the glacier's size, its altitude, and its local climate. Small, low-elevation glaciers are the most vulnerable and are disappearing first. Many in the Alps, the Rockies, and the Andes have already vanished, their names remaining on maps as ghostly reminders of a colder past. Larger glaciers and ice sheets are more resilient, but they too are losing mass at an accelerating pace. The IPCC reports conclude with high confidence that current rates of mass loss from glaciers and ice sheets are unprecedented for at least the last 2,000 years. This is not a natural cycle. While glaciers have advanced and retreated throughout Earth's history, the current, rapid, and globally synchronized retreat is happening far too quickly to be explained by the slow wobbles of the Milankovitch cycles. The forcing agent is the dramatic increase in anthropogenic greenhouse gases, which is causing the planet to retain heat at a rate that the cryosphere cannot withstand. The Great Melt is a direct consequence of the Great Heating. To walk in a glacial forefield is to walk in a landscape of recent death. The air is quiet, the ice is gone, and all that remains is the scar it left behind. There is a profound sense of absence, but this is not a quiet passing. The meltwater streams flow faster and louder than ever, carrying away the substance of the glacier in a final, rushing exodus. The era of retreat is a poignant and sobering chapter in the story of ice. It is the phase where the river of ice, after millennia of patient flow, begins to evaporate before our eyes, leaving us with the exposed bones of the mountains and a growing awareness of the world we are creating. The great melt is the sound of a balance, held for thousands of years, being broken. There is a sound to the end of an age. It is not a crash, but a drip. A persistent rhythmic patter that begins as a whisper and grows into a chorus. On the surface of a glacier in the summer sun, the air is filled with the music of meltwater. This is the glacier's voice in its final act, a language of liquid that speaks of transformation, of release, and at times of terrifying power. To listen closely to a glacier is to hear its lifeblood escaping, and to understand the profound hydraulic forces stirring within its silent, frozen heart. The most elemental sound is the solitary drip. From the tip of an icicle hanging from a serac, from the edge of a small supraglacial pool, each drop falls with a soft, metallic plink. This is the sound of the ice yielding molecule by molecule to the sun's energy. It is a gentle, almost meditative sound, the starting point of a journey that will grow in volume and intensity. As the day wears on, these individual drips multiply. They coalesce into tiny rivulets that trickle down the ice, their sound a delicate gurgle, like a miniature stream finding its path. Soon, the soundscape transforms. The trickles merge into braided streams that flow in channels carved into the ice itself. These are not quiet brooks. They are milky turquoise torrents rushing with purpose. The sound is a low, continuous roar, the sound of water flowing over and through a substance that is itself both the riverbed and the river. The water is heavy with rock flour, giving it a viscous, substantial quality that seems to deepen its acoustic presence. In places, these streams vanish into the ice, pouring into a vertical shaft known as a moulin. The sound here changes dramatically. The cheerful gurgle of the surface stream is swallowed by a deep, thundering plunge, a booming echo that rises from the abyss as the water catapults into the glacier's dark interior. It is the sound of the glacier drinking itself. Beneath the surface, in the hidden world of the inglacial and subglacial plumbing system, the water moves under pressure. It flows through tunnels and along the bedrock interface, its sound muffled by millions of tons of ice. But this hidden water is the glacier's great lubricant, and its pressure can build to explosive levels. This brings us to the most fearsome sound a glacier can make, the roar of a jökullaup, an Icelandic term meaning glacier run. A jökullaup is a sudden, catastrophic, glacial outburst flood. It occurs when a large body of meltwater, trapped either beneath the ice or in a marginal lake, is released abruptly. The trigger can be the failure of an ice dam or the rapid draining of a subglacial lake whose water pressure has finally lifted the glacier enough to open a seal. The sound that precedes such an event is often a deep, unsettling rumble from within the ground, a groaning of the ice as it strains to contain the pent-up water. Then the dam breaks. The sound is not just loud, it is overwhelming. It is a low-frequency wall of noise that vibrates through the entire valley, a crushing, grinding roar of water, ice, and rock. It is the sound of a tidal wave born from ice, a force that can move houses-sized boulders and strip a valley to bare bedrock in hours. The jökullaup is the glacier's most violent utterance, a reminder that the seeming stillness of the ice conceals energies of biblical proportion. To hear it is to understand that a glacier is not just melting passively, it can die in a paroxysm of elemental fury. Yet after the flood passes, the smaller sounds return. The drip, the trickle, the gurgle. But now, to the attentive ear, they carry a different meaning. They are no longer just the sounds of summer, they are the sounds of a glacier in distress. The symphony of melt is playing at a crescendo that is historically unprecedented. The constant drip is the measure of an imbalance. The stream's rush is the sound of a reservoir being drained too quickly, and the distant rumble of a rockfall from a newly unstable valley wall is the sound of a landscape adjusting to the absence of its icy anchor. The sound of melting is therefore a paradox. It is the sound of life-giving water being released to rivers and ecosystems downstream. But it is also the sound of loss of a world of ice fading into memory. It is the sound of a system unraveling. To stand on a glacier in the summer is to be surrounded by this aqueous chorus, a beautiful, haunting melody that tells the story of a transformation happening too fast. It is the background music to the Great Retreat, a soundtrack of drips, streams and occasional thunderous floods that marks the passing of the ice. The glacier is gone. After millennia of presence, its cold weight, its slow flow, its abrasive touch have vanished from the valley. What remains is a new landscape, raw, unstable, and strangely quiet. This is the world after the ice, a terrain in its infancy, grappling with the sudden absence of the force that defined it. The legacy of a lost glacier is not merely an empty space. It is a complex and dynamic chapter of geological adjustment, ecological opportunity, and profound change. The vanishing of the ice is not an end, but the beginning of a new story for the land. The most immediate impression is one of starkness. The valley floor is a canvas of bare rock, scraped clean and polished to a dull sheen. Scattered across it are the chaotic deposits of the glacier's final moments, mounds of till, the winding ridges of recessional moraines, and the immense, solitary erratics that sit like forgotten monuments. This is a paraglacial landscape, an environment that is undergoing rapid adjustment to the removal of its glacial ice. The land once pressed down by billions of tons of ice is now free to rebound. This isostatic uplift is a slow, persistent rising of the crust, a sigh of relief that will continue for thousands of years, subtly tilting the land and altering drainage patterns. Without the supporting buttress of ice, the valley walls are unstable. The glacier's abrasion has steepened them to precarious angles. Now rockfalls and landslides become frequent. The sound of scree tumbling down a cliff face replaces the groan of moving ice. The landscape is literally crumbling, seeking a new, more stable angle of repose. The streams flowing from the retreating glacier's snout are laden with this freshly liberated sediment. They braid across the valley floor, shifting their courses daily, depositing vast sandy plains. The water, once a consistent, milky flow, becomes volatile, a torrent during the summer melt, a trickle in the winter. But into this instability, life begins to cautiously return. The process of ecological succession begins with the hardiest of pioneers. The first colonists are often lichens and mosses, organisms that require no soil. They attach themselves to the bare rock, secreting acids that slowly break it down. Their death and decay over decades create the first, thin, fragile layer of organic soil. This allows hardy alpine plants to take root, saxifrages, cushion plants, and grasses that can withstand the harsh, exposed conditions. They are followed by shrubs and eventually, if the climate allows, by trees. The legacy of the ice shapes this new ecosystem in direct ways. The moraines, with their well-drained soils, often become natural terraces for vegetation. The kettle lakes that form when buried blocks of ice melt within the till become focal points for life, attracting insects, birds, and mammals. The erratic boulders provide shelter from the wind and sun for seedlings. The new landscape is a patchwork of habitats created by the very debris the glacier left behind. For human communities, the vanishing of a glacier redefines their relationship with the mountain. Water sources become less reliable. The steady, summer-long flow from the ice is replaced by a shorter, more intense surge of snowmelt, followed by drought. The risk of glacial lake outburst floods, GLFs, looms large as moraine-dammed lakes at the glacier's toe can burst catastrophically. The very geography that defined a region's identity and resources is transformed. Yet there is a stark beauty in these newborn landscapes. The new lakes, with their stunning turquoise color from suspended rock flour, are set like jewels in the rocky wilderness. The exposed geology reveals folds and faults in the bedrock that were hidden for millions of years, offering a fresh page for geologists to read. The silence is different now, not the silence of frozen stillness, but the quiet of a land catching its breath. The legacy of lost ice is therefore a double-edged sword. It is a landscape of fragility and hazard, but also one of resilience and rebirth. It demonstrates the Earth's relentless capacity for change. The glacier's work is done. It has carved the theatre. Now the slow, patient processes of weathering, erosion, and colonization will take over, softening the sharp edges, filling the basins with soil, and eventually cloaking the raw rock in green. The vanished glacier leaves behind a wound, but also a seedbed. It is a poignant reminder that all landscapes are temporary, and that the Earth is always, patiently, remaking itself. The river of ice has flowed away, but the valley it carved will tell its story for eons to come. For most of human history, glaciers existed at the edge of our world, both geographically and imaginatively. They were the inaccessible frozen fastnesses of the highest mountains and the farthest poles, realms of spirits and mysteries, inspiring awe and fear in equal measure. Our relationship with them has been a long and evolving story, a journey from mythical reverence to scientific inquiry, and finally to a stark realization of their critical importance to our survival. Glaciers have shaped human cultures, and now humanity is shaping the fate of glaciers. To ancient and indigenous peoples living in their shadow, glaciers were often seen as animate, powerful beings. In the Andes, the great white peaks were, and still are, revered as Apus, mountain spirits that control the weather and water. Offerings were made to these icy deities to ensure good harvests and to appease their tempers, which could manifest as avalanches or droughts. In the Himalayas, glaciers were considered the sacred hair of Shiva, a source of purity and spiritual power. In Norse mythology, the icy realm of Niflheim was one of the primordial worlds, a place of freezing mist and cold that existed before the creation of life. These were not landscapes to be conquered, but to be respected. They were the abodes of gods, and their slow, inexorable movements were interpreted as divine actions. The scientific revolution began to change this relationship. The pioneering work of naturalists like Louis Agassiz in the 19th century introduced the radical concept of ice ages. The idea that glaciers had once been vastly larger, scouring continents and shaping entire landscapes, was a profound shift in understanding. It moved glaciers from the realm of myth and local phenomenon to a central force in Earth's history. They were no longer just static, frozen features. They were dynamic shapers of the world. This was the beginning of a more utilitarian view. Glaciers became subjects of study, their motions measured, their depth sounded. They were puzzles to be solved. This scientific curiosity soon merged with practical necessity. As the role of glaciers as natural water reservoirs became clear, their value to human societies was quantified. The steady, reliable release of meltwater during the dry season is the lifeblood for millions of people. In the Indus Basin, the Ganges-Brahmaputra system, and the arid regions of the Andes, glaciers act as a buffer against drought. They are not merely scenic wonders. They are critical infrastructure. This has created a deep, practical dependency. The water for irrigation that grows the crops fills the reservoirs that generate hydroelectric power and supplies the taps of megacities like La Paz and Kathmandu is, in large part, glacial meltwater. The glacier became a resource, an unthinking, reliable servant to human civilization. The 20th and 21st centuries have added a new, more complex layer to this relationship: glacier tourism. What was once the domain of a handful of explorers and scientists is now a global industry. People travel from across the world to walk on glaciers, to witness their carving fronts, and to experience their grandeur. This has brought economic opportunity to remote mountain communities, but has also introduced new pressures. The very act of visiting a glacier with its associated carbon footprint contributes to the warming that threatens the glacier's existence. It is a poignant paradox. We are drawn to see these icy wonders before they vanish, and in doing so, we accelerate their departure. Now our relationship is entering its most critical phase. The era of seeing glaciers as a stable, infinite resource is over. Climate change has transformed them from dependable partners into vulnerable indicators of global crisis. The same scientific tools we use to understand their past are now used to project their future, and the forecasts are alarming. The conversation has shifted from how we can use glaciers to how we can possibly adapt to their loss. The mythical Apus are retreating. The sacred hair of Shiva is thinning. This has sparked a new form of reverence, one based not on superstition, but on science and a visceral sense of loss. The concept of solastalgia, a form of emotional distress caused by environmental change, is felt deeply by those who watch a familiar glacier disappear within their lifetime. Artists, filmmakers, and writers are increasingly drawn to glaciers as symbols of fragility and the profound changes underway on our planet. The story of glaciers and humanity is a mirror of our own evolution. We began with fear and reverence, moved to understanding and exploitation, and now face a future of managed retreat and adaptation. The river of ice that was once a god, then a reservoir, has now become a teacher. It is teaching us about the consequences of our actions on a planetary scale. It is showing us that the resources we took for granted are finite. And in its silent, majestic retreat, it is delivering one of the most urgent messages of our time, that the balance between humanity and the natural world has been broken, and that the ancient heart of the mountains is beating a fragile, fading rhythm.